Hello and welcome to the last video of the chemical bonding discussion series. In this video, we will be discussing molecular polarity. So knowing the shape of the molecules helps us to understand the physical and chemical behavior of a substance. So one of the effects of molecular shape is molecular polarity, which also influences the melting and boiling points as well as the solubility, reactivity, and even biological functions. If you can recall from our previous lessons, we have discussed that covalent bond is polar when the atoms have different electronegativities and thus share the electrons unequally. In terms of the molecules, we can determine if a molecule is polar or nonpolar depending on the following. The first one is the polarity of the individual bonds, and the other one is the overall shape of the molecule. We say that a molecule is nonpolar if they have no polar bonds, or if they have bond dipoles that cancel, or if they have individual bond dipoles that cancel. Later, I will be showing you here how dipoles cancel. And then when we say polar molecules, they generally have only one polar bond or individual bond dipoles that do not cancel, which is the opposite of nonpolar molecules. In here, we have a carbon dioxide molecule as our example. In carbon dioxide, it has polar bonds, however, it is considered a nonpolar molecule. Why? In this example, the electronegativity difference between carbon with an En value of 2.5 and oxygen with an En value of 3.5 makes this carbon and oxygen bond polar, with the electron density being pulled towards oxygen. However, carbon dioxide is linear, so the bonds point 180 degrees from each other. And since the two bonds have polarities that are equal in magnitude but opposite in direction, their polarities cancel. So this is an example of bond dipoles that cancel. Therefore, it will result in no net dipole moment for the molecule. So in general, this would be a nonpolar molecule because there is no dipole moment for the atoms. So in this type of molecules that have polar bonds, it will exhibit no net dipole moment if all surrounding atoms are the same and are arranged symmetrically around the central atom, and an arrangement that occurs when all corners of the electron group arrangements are occupied by atoms and there are no lone pair on the central atom. In our another example here, we have here water, which has polar bonds as well, but unlike carbon dioxide, it is classified as a polar molecule. How? So water has two polar bonds, as I have said earlier, and in each oxygen and hydrogen bond, the electron density is pulled from hydrogen with an En value of 2.1 towards oxygen with an En value of 3.5. So their bond polarities technically don't cancel each other because the molecule is V-shaped. The bond polarities actually reinforce each other. We call it reinforcement. So the bond polarities are partially reinforced, making the oxygen end partially negative and the other end, which is the hydrogen ends, partially positive. So this will make an overall dipole moment, and we can say that water is a polar molecule. So here are the other examples of polar and nonpolar molecules. Remember that when there is no net dipole or all dipoles cancel, it is called the nonpolar molecule. While if all dipoles reinforce, it will be considered as a polar molecule. So let's work on some examples. So for each of the following, use the molecular shape and electronegativity values and trends, which can be found on your book, figure 9.19, page 294, to predict the direction of bond and molecular polarity if present. So we have the following compounds: ammonia, boron trifluoride, and carbonyl sulfide. So our plan is to draw and name the molecular shape and mark each polar bond with a polar arrow pointing towards the atom with the higher electronegativity value. If bond polarities balance one another, the molecule is nonpolar. If they reinforce each other, we show the direction of overall molecular polarity. For our first example, ammonia, remember that the molecular shape of our molecule based on our previous video would be trigonal pyramidal. So in here, nitrogen is more electronegative than hydrogen. So the bond polarities will point towards nitrogen. And partially, as you can see from the diagram, they will reinforce each other. Thus, the molecular polarity points toward N, and we can say that ammonia is polar. For our second example, on the other hand, we have boron trifluoride with the molecular shape of trigonal planar. And as you can see here, fluorine is more electronegative than boron. So it will make the bond polarity points toward F or fluorine. However, the bond angle here is 120 degrees. So the three bond polarities balance each other or they cancel each other. Therefore, boron trifluoride has no molecular polarity, making it a nonpolar molecule. For our last example, we have carbonyl sulfide. So we have here a linear molecule. With carbon and sulfur having the same En values, we can say that the bond is nonpolar. However, between carbon and oxygen, the bond is polar because they have an En difference of 1. Therefore, there is a net molecular polarity towards oxygen. Since there is a dipole moment here, we can say that carbonyl sulfide is a polar molecule. And that ends our discussion for molecular polarity. Thank you for listening.